Thank you very much. It's not all that different. We're on the last slide, though. Maybe you can go to the first slide. I'm done. Thank you so much. That was a great talk. The stage is set, and I can leave. You got to go to slide number 1. Ah, beautiful. There we go. Okay. So I'm going to talk today about GEDI, the Global Ecosystems Dynamics Investigation. Here's a list of my co-authors, part of the GEDI science team, and their institutions. So as we've been hearing today, we're in this exciting new era of remote sensing, radar remote sensing of the land surface. And one of the most dynamic aspects of the land surface are forests. And one of the things we've been missing is getting this vertical forest structure, the 3D structure. And it's important for a lot of applications. CEOS, which is basically an advisory agency to NASA and other international space agencies, really drove home this point by having a very strong recommendation that to go along with all these exciting new radar missions that we're getting online, such as NISAR, such as Tandem-X, Tandem-L, ALOS-2, which is up there, the PBN biomass mission, that we need to get vertical structure from LiDAR. We've been trying a long time to have a satellite to get us this information, and fortunately we finally now are going to have it, GEDI LiDAR, and this is what I'm going to talk to you about today. So GEDI is an Earth Ventures instrument. It's a joint collaboration between the University of Maryland and NASA Goddard Space Flight Center as part of NASA's Earth Ventures program. We're selected in August of 2014. These are PI mode missions where my institution, the University of Maryland, has control of the mission from beginning to end, essentially. We're going to be putting a multi-beam LiDAR on board the space station, and we hope to deploy sometime in early 2018. Now, we have a set of important science questions we're trying to attack with GEDI, some of which overlap with what we heard about the Helmholtz Alliance, what we've heard about NISAR. The first question that we're attacking here is, what is the carbon balance of the Earth's forests? And to answer that question, we want to quantify two things. We have two objectives. The first is to quantify what is really on the surface now in terms of forest biomass, or its above ground carbon. And then the second objective is to look at disturbance and recovery over the last 2 decades and understand what the balance has been of loss of carbon through disturbance and its subsequent regrowth. To understand this a little bit better in terms of the carbon cycle, we can look at what is now a relatively iconic figure from the Global Carbon Project. And here you see the different elements of the carbon cycle. So we have this large input of fossil fuel emissions and from cement production of atmospheric CO2. And about half of that, unfortunately, stays in the atmosphere. So the atmosphere serves as this kind of atmospheric sink, and that leads to this, again, accumulation of the greenhouse gas of CO2 there, which is bad. About the other 50% is evenly divided, more or less, between the ocean sink and the land sink that you see there. Now, if we look more closely at the land surface, these are the two parts of the puzzle we're trying to nail down with GEDI. We want to know what is the emissions, or what are the emissions that have taken place when we have land use change, we burn trees down, that makes its way into the atmosphere as CO2, but forests also serve as this important land sink. We don't know these two numbers very well, the uncertainties notwithstanding. They're usually calculated as a residual of all the other terms in the carbon cycle that we know much better. So GEDI will provide the data to help us answer what these numbers are and help us make prognostic predictions going forward. And that gets us to our second question, which is, how will the land surface mitigate atmospheric CO2 in the future? And so what we want to quantify is the carbon sequestration potential of forests going future. The U.S. Forest Service has estimated that U.S. forests have absorbed an astounding 15% of industrialized emissions over the last century or so. And the reason for that primarily is because of historical land use change, where we've had abandoned farmlands. These farmlands have filled up with trees, which have absorbed a lot of carbon, plus historical practices in forestry. We don't know whether or not these North American forests will continue to act as sinks, and we certainly don't know what's happening internationally in tropical forests as well. And so one of the things we need to do is get the data so that we can initialize prognostic models to ask questions about what will happen 50 and 100 years in the future with regards to the land sink. And then the third question that we want to answer is, how does forest structure impact habitat quality and biodiversity? And again, to answer that, we have as an objective to quantify vertical forest structure and its relationship to biodiversity. Biodiversity is under great threat globally, and one of the strongest factors that impact habitat quality and biodiversity are the vertical structures of forests, because we have different vertical niches, as well as the spatial pattern. What we've been missing thus far is a comprehensive set of observations of that vertical structure that we can relate to biodiversity estimates. So here is the GEDI LiDAR instrument. It's really a geodetic instrument. It's a laser altimeter. It's comprised of 3 lasers. The lasers fire laser beams towards the surface. They get collected by a telescope. We also have star trackers on board. We have GPS. We have inertial motion units on board, all of which help us locate the beam relatively accurately on the ground. As Joseph Kellendorfer said, we need to know where those measurements are from if we're going to relate them and fuse them with radar information. We also have a gimbal, which means that we can point the instrument left to right so that we can fill in any types of gaps. These lasers that are flying are arguably the most tested lasers that have ever gone into space, so we have a high degree of confidence that these lasers are going to work and work for a long time. So if you're not familiar with LiDAR measurements, we start out by firing a beam of laser energy towards the surface. In our case, when that beam hits the surface, it's about 25 meters across. Some of that laser energy, as it penetrates the canopy, reflects off the leaves and branches, and it continues down towards the ground. And so what we get back is this return waveform, where the amplitude of the waveform is a function of how much canopy material there is at any height, how many leaves and branches there are. We also get the ground below the canopy, so we get a very good ground elevation. We'll get the canopy profile, and we can get the canopy height by knowing where the first return is and where the ground is. 15 billion, that's a huge number, right? 15 billion is the number of observations that we're going to get over land from GEDI, which is order of magnitude better than what we can do. Now, the reason we can get so many observations is we have a relatively innovative design of lasers and of ground track sampling. And so we have 14 tracks along the ground. Each one of these circles is one of the 25-meter spot sizes from GEDI. And we have 500 meters between spots. And then across the entire swath width, this is 6.5 kilometers. Now going a long track towards the vertical direction on the screen, we have 60 meters between spots. None of this is to scale. So basically, we skip every other footprint. Now we have these 3 lasers here. The 2 outboard lasers are split into 3 beams each. And we keep 1 laser, and it's not split. It's a full power laser. So at any one time, we have 7 beams hitting the surface of the Earth. We then electro-optically dither these beams to bounce them back and forth so that we get 14 ground tracks that you see here. So we have 3 lasers, 7 beams, and 14 ground tracks, 15 billion observations per year. So we will be deployed on the International Space Station. We will be up there near the front. We'll probably get up there on something like the SpaceX Dragon capsule. We'd be in an unpressurized trunk behind it. We're this coffin-shaped thing that's in there, so we'll get a ride up there. And we're actually deployed on the Japanese experiment module out there on the exposed facility. So the robotic arm grabs us from our grappling hook and puts us in an open spot. It's actually not that spot. It'll be a spot on the other side. It's spot number 6, in theory. Okay. So our science approach is relatively straightforward. Because we're an EVI mission, we have to be self-contained in terms of our science that we're accomplishing. But I want to stress that when you combine our data with these radar observations, we can do a lot more science. It's just not part of our, quote, science approach for within the EVI program. So we start out with GEDI waveforms, and this is the sole observable of the instrument. This is all we get back from the instrument. And then we run those data through our algorithms to get canopy height metrics and canopy profile metrics. Those are immediately related to biodiversity and habitat metrics, and lets us attack our objective on relating those to biodiversity issues. And we make those at the footprint level, and we also grid them to 500-meter grid spacing. We take that same data and we run them through 2 classes of models. One are empirical models, and that second class of model is a physically based ecosystem model, the ecosystem demography model. Each of those models produces a grid of above-ground biomass at 500-meter spacing. And so this gets us at the present. We can understand what the current biomass is of the surface forest. The next objective is looking into the past. And we combine this above-ground carbon data with Landsat disturbance data over the past 20 years. And so we'll look at the net balance between disturbance that's happened and then the subsequent regrowth that will answer an important piece of the puzzle for the carbon cycle. And so that's looking into the past, and then we finally look into the future by using a prognostic ecosystem model, again, the ecosystem demography model, which we initialize with the GEDI LiDAR data. And we ask questions about how much carbon the land surface will sequester going forward in the next 50 to 100 years. This particular model serves as the land surface basis of general climate models, and so it can serve as a very accurate way to ask these what-if questions. So, for example, should we plant every soccer field in the United States with trees? Or should you plant trees out in your city streets or in your backyards? What impact will that have on the carbon cycle? To answer those kinds of questions under changing land use and changing climate, where you have increased disturbance from fire and hurricanes, requires that we marry this type of data with a prognostic model. So now getting to the fusion of NISAR with GEDI. GEDI is going to provide really a sea change in terms of calibration data that are available to use with missions like NISAR and other radar missions as well, to really greatly extend the ability to do some of the science that we'd like to accomplish in terms of ecosystem structure. Here's, for example, is a map of pan-tropical biomass made by Sasan Sachi. This map used the best data that they had, which was ISAT data, LiDAR. And when we have GEDI data, we will have 3 orders of magnitude more observations to fuse with radar data from NISAR or from ALOS than we had to make that map. And so we'll be able to do a much better job, not of just pan-tropical mapping, but of temperate mapping as well. And so if you consider the fusion of both of these, of GEDI with NISAR and other radar missions, what you have is the ability for GEDI to raise this limit in terms of what NISAR can map. NISAR is going to map low biomass areas. If you combine it with GEDI, we'll be able to push that number higher. Likewise, NISAR provides a mechanism by which we can get to finer resolution than we could by ourselves with just using GEDI, which is limited to this 500-meter grid spacing. Now, GEDI does not observe the boreal forest because the latitude limits of the space station, but NISAR should give us very good information on boreal biomass. So when we combine NISAR estimates of boreal biomass with the temperate and tropical estimates we'll get from GEDI for biomass, we'll have a true and comprehensive global observing strategy. Likewise, as Joseph mentioned, we will get annual disturbance maps from NISAR, but they'll be classified maps. They'll tell us whether something was disturbed or it wasn't. We can add the GEDI data to those maps so that we can quantify how much biomass was lost. And unrelated to ecosystems, GEDI will provide many observations over temperate glaciers. For example, we'll have 4 million observations over the Patagonian, the North and South Patagonian ice fields, which is arguably, I think, about the 3rd potential largest contributor to sea level rise. And so we'll be able to add a lot of science as well in the cryospheric realm. Lastly, we have a formal collaboration with the German aerospace agency, DRL, to explore fusion with Tandem-X. Tandem-X provides high-resolution topographic data. It has 2 satellites. These are X-band and the X-band satellites. And using interferometric methods, others have shown that there is some potential for using X-band interferometry from Tandem-X to get at some aspects of canopy structure. And the fusion of the 2 is what we're going to be exploring. And so the possibility of combining these is very exciting. Here's one example from DLR. This is over the now famous Traunstein forest in Germany, where the top image is the actual forest heights from LiDAR, and the bottom image is their reconstruction using Tandem-X. One of my own students has also looked at this over temperate forests, over Hubbard Brook experimental forest, where we simulated GEDI tracks going across the basin. And then we looked at Tandem-X data and ran using dual pole data, used an RVOG model to then make a continuous map with relatively good estimates of height. So to conclude, you already saw this slide. The stage is set, and we're entering, again, this exciting era of radar remote sensing. When we combine it with what we're going to get from GEDI as well as other missions, we'll be able, for the first time, to have a comprehensive view of ecosystem form, ecosystem function, and ecosystem structure. Thank you very much.
Thanks, Ralph. Any questions? Maybe one or two questions? Yes.
Yes, absolutely. So that, because I'm talking, the question was, are there any plans to combine this with ICESat-2? In the interest of time, I didn't list ICESat-2, but it's very, very important. It'll provide beautiful data on the boreal regions as well as possibly savanna regions. And so when you combine NISAR with ICESat-2 with GEDI, it's a really exciting period for putting them all together in terms of ecosystem structure.